All right, welcome back to part 2 of material testing. So we left off analyzing the tensile test stress strain curve. So the offset yield strength defines the stress required to produce a tolerable amount of permanent strain. And this is set by a designer or manufacturer. So how much force can I use to deform the object just a little bit, but still keep all of its functionality? Plastic deformation is unrecoverable beyond the elastic limit. So when the load is removed, meaning when I don't apply the force anymore, only the elastic deformation will be recovered. So in this case, the strain is permanent because we've applied too much force to it. So this represents a failure because the part dimensions will now be outside of allowable tolerance. Again, it's not going to have the functionality or fit in with any other parts that you might have in your design or in your assembly. So the deformation is where the test sample gets longer. So when you're watching this, that's when the test sample starts to stretch, just kind of right before it breaks. Your cross-sectional area decreases, and your load-bearing ability actually increases. How's the material getting stronger? Well, the material is getting stronger because the weakest point becomes stretched, but that actual weak point becomes stronger, and it's very slight. Once you get to the elongation part of this curve, the force applied doesn't go up that much. So the weakest point is stretched, and this keeps occurring until the decrease in area overcomes the increase in strength. So tensile strength, this is where the load-bearing ability peaks. So when you hear stuff about the tensile strength of varying objects or materials, this is what's going on. This is where you get this necking or a visible decrease in the cross-sectional area of the material. So failure comes at the end of the graph, where something finally pulls apart and then the force applied on it stops. And so then the test is over. And ductility is the amount of plasticity before the fracture. So the greater the ductility, the more material can be deformed. So the greater this curve right here, the more strain you can put on the material before it breaks. So let's compare the material properties of these three metal samples. So brittleness is material failure with little or no ductility, not necessarily a lack of strength. Think concrete or your porcelain type stuff and so on. So that's the graph on the right. All right, toughness is the work per unit volume required to fracture a material. So this is the total area under the curve from the test. It looks at both strength and ductility. Compression tests are similar, but the test samples have to have a large cross-sectional area because you don't want them to bend. So instead of pulling something apart here, you're pushing something together. This is very useful when you're looking at building materials and stacking things on top of one another with vertical loads. Hardness testing is resistance to scratching, wear, cutting, drilling, etc. So essentially you create a crater within the material, and then you measure that crater and compare it to some known values. Same thing with a rock wall test. You're measuring how far something can be forced into the material. We're not going to get into compression and hardness too much. So that's the end of the material testing screencast. We'll walk you through the calculations, how to figure that out in class.